Today we're going to be completing the acid and base notes, and we're going to start off by calculating pH. In 1909, Sorensen developed the pH scale, which is based on hydrogen ion concentration. In order to find the pH, what you would do is take the negative log of the H plus concentration. If you were trying to find the pOH, you would find the negative log of the OH minus concentration. And this can easily be done by plugging into your calculator. When you get your answer for log of H plus or log of OH minus, you should always have a negative answer, which is then canceled out by the negative that's out in front over here. So pH and pOH will always be a positive number. Down here you can see that pH plus pOH is equal to 14, which means if you are able to find the pH, you can easily switch it to pOH using that equation, and vice versa. These are two more examples of the pH scale, which runs from 0 through 14. This is very similar to the one that you were given on the first slide of the notes. So this is just something that you could use if you have to figure out if something is acidic or basic based on pH. Alright, for our first sample problem here, we're trying to find the pH, and we are given the hydrogen ion concentration, or H+. So we know that pH is equal to the negative log of H+. So at this point, we could just plug into our calculator the log of 4.2 times 10 to the negative 10th power. And when we do that, we end up with a negative answer. We end up with negative 9.4 for this. And then we have another negative sign here, so they cancel out. So this ends up being a pH of 9.4. Now I mentioned before that pH plus pOH is equal to 14. So let's say hypothetically here they had also asked for pOH. What I could easily do is take 14 minus the value of the pH, which was 9.4. And then I would get my pOH. Alright, for this sample problem we are simply converting between our H plus concentration and pH for each of these. So it's just a matter of plugging it into your calculator. So you would press the log function. If you're using the yellow calculators that we use in class, you would click the second button on the top left corner, the PRB button towards the center, and then you would press enter, and that should bring up the log function on your screen. So when you type this in, you should end up with a pH of 4. This one would be a pH of 2.8, and this one would be a pH of 12. So if you're trying to complete practice problems at home, I would suggest a Google calculator if you do not have a scientific one of your own. It works fairly well, and for that one there's a log function towards the middle left side, and you just click that button and then type in your answer in scientific notation. Alright, indicators we've already mentioned a little bit in the first section of the notes. An indicator is something which gives a visible sign in the presence of an acid or a base, so it helps us to kind of pinpoint what the pH is. There's different types of indicators, one being universal. So when you put universal indicator into an acid or base, it will fall somewhere on a scale based on what the pH is. Other examples are litmus paper, which we talked about when we first introduced the properties of acids and bases, and also phenolphthalein, which is typically used in titrations. So these you will see within your labs in this class. We don't tend to use methyl orange, but that is another possibility for an indicator. Alright, so to close out our notes, we're going to be doing a couple of example problems for titration and explaining how this process works. Within a titration, you have an acid and a base which are mixing together to produce salt and water. Within this reaction, the acid and base are canceling each other out to make this harmless substance, salt and water. So we also talked about this when we did safety at the beginning of the year. So for example, if you spill some acid on the floor, you could put a base on top of it to neutralize it. The equivalence point is the point where the number of moles of hydrogen is equal to the moles of hydroxide, where they are completely canceling each other out. The formula that we are going to be using to complete our titration problems is M1V1 equals M2V2, which we could also write as MAVA equals MbVb. These two equations could be used interchangeably. I tend to write it this way because then you have your acid side and your base side. And then students tend to be less likely to mix up the molarities or the volumes and put things on the wrong side. So you have an acid side and a base side. All right, here are the steps for a titration. So typically you would have a measured volume of an acid. So maybe I know it's 25.0 milliliters or 50.0 milliliters. And you also have an unknown concentration of this acid. So I know how much acid I have, I do not know how strong it is. A titration will allow us to figure out how strong that acid is. You would start off by putting several drops of the phenolphthalein indicator into your Erlenmeyer flask and swirl it around. Initially, this doesn't do anything. When phenolphthalein is exposed to an acid, it remains clear. Then you would have something called a burette, which is filled with a base solution of known molarity. So I know the concentration of that. So that would be Mb. Then you would open the valve of the burette slowly, and you would add some of the base into the Erlenmeyer flask. As you do that, you're going to see little splotches of purple as the base is hitting the phenolphthalein and reacting with it. But as you swirl, they should go away because the acid is going to continue to react with the base. So it kind of disrupts any of the hydroxide ions that would be floating around. Eventually, once the base starts to overpower the acid, you're going to have some hydroxide which is left over. And that's going to give it a purple color. So here you can see that process. So this is my burette. And I start to add some of my base into my mixture of acid and phenolphthalein. Initially you get this small little purple dot, but as soon as you swirl around, it goes away. If you continue to add in more and more base, if you do it perfectly, you get to this point right here where you have a very faint pinkish purple at the end point. Now, typically when people first try to do a titration, they tend to be a little heavy-handed and they add a little too much base. So if you go too far, you would see a deep purple and it would not dissipate as you start to swirl it around. So if you were going to go past that point where you add too much base, that could be easily fixed. You do not have to do the experiment over. You would have two of these burettes, one with base in it and another one with acid. So if I add more acid to this mixture here, the acid would help to neutralize some of the base that's in there, and then you can go back towards the end point. So when you first do a titration, you may end up going back and forth a little bit until you get to that perfect point in the middle. Alright, for this problem, we're trying to figure out how many moles of sulfuric acid are required to neutralize 0.5 moles of sodium hydroxide. So this is kind of like a titration problem, but simpler. We don't have any volumes involved. We just have the mole part of molarity. You may remember that molarity is equal to moles per liter. So here we're just kind of skipping out on the liter part. We're just given moles. So essentially this is really just a stoichiometry type problem. So I have my 0.5 moles of sodium hydroxide. And I'm trying to figure out how many moles of sulfuric acid would react with that. So I can do that with a one-step conversion. So I'm going to cancel out my moles of sodium hydroxide on my way to moles of sulfuric acid, which is H2SO4. This is sulfate, and sulfate, the ATE ending goes to IC when it's in an acid. For the numbers here, I get this from the balanced equation. So I have 2 of my sodium hydroxides for every 1 of my acid. So this comes out to 0.25 moles, which could then be rounded for significant figures. So I would round that to 0.3 since I started with one significant figure here. Alright, now for this titration problem, we're going to use that formula that I introduced earlier. So MAVA equals MBVB. And you may notice that this is very similar to one of the gas laws that we covered, Boyle's law, where you have 4 variables in a straight line with 2 variables on either side. When you're trying to set up any of these types of problems, I would suggest that you write down each of the variables that are either going to be known or unknown, and you pull those variables out of the word equation. So we'll make it easier to solve. We have a 25 milliliter solution of H2SO4. The H2SO4 tells you if it belongs on the A or B side. This is an acid. It's beginning with a hydrogen. So that means I have 25 milliliters for my volume of acid. It is completely neutralized by 18 milliliters of 1 molar sodium hydroxide. OH is a component of a base. So I have 18 milliliters and 1.0 molarity. What is the concentration of the acid? That's Ma. So from my original equation, MaVa equals MbVb, I know that I need Ma by itself. So I divide both sides by Va. That cancels out. And now it's just a matter of plugging in the numbers. So I have 1.0 times 18 divided by 25. My milliliters cancel with milliliters, and I'm left with just a concentration. So that looks like that was set up correctly, since that's what I was looking for. When you plug this in and round for the two significant figures, you end up with 0.72. That's capital M for molarity. Alright, so for our last problem here, we're going to go just in the opposite direction. So this time we're going to be looking for milliliters instead of a concentration. So I'm going to write out each of my variables here. So I have Ma, Va, Mb, and Vb. How many milliliters of acid? So I'm looking for volume of acid. I'm starting off with 0.45 molar. We'll neutralize 25.0 milliliters of 1.00 molar KOH. So KOH is our base, so these are both on the base side. I write out my equation and I move my variables around so I can get Va by itself. So I divide both sides by Ma, and that cancels out. When I plug in the Mb, I have 1.00 molarity and 25.0 milliliters. I'm dividing by 0.45 molar. The molarity cancels out here. I'm left with just milliliters, which makes sense. I'm looking for a volume, Va. When I multiply all this across and round for two significant figures from the 0.45, that comes out to 56 milliliters. That would be your final answer. So if you were able to get through gas laws and you were comfortable with doing Boyle's law, this is basically the same thing. So you're not doing anything different mathematically. You just have a different variable. You have concentration this time instead of pressure. All right, so for our final wrap up, if you're still having a hard time with naming acids, so the rules for bonding to a regular element versus polyatomics like nitrate or nitrite, make sure that you check out the Tyler DeWitt video that we had assigned for homework. There's a crash course video on acid-base reactions that I didn't assign, but it is helpful, so if you want, you can watch that. It's on the YouTube channel. There's a video from the Fuse School, which will go through indicators, so you can watch that. And finally, there's a simulation, which you can see the link for right here. So if you follow that link, you can go through a titration on the computer. And it also shows you a curve here for the change in pH as you add acid or base. If you need any other extra help before the unit quiz, make sure that you come in to see me either in the morning or afternoon.